Welcome to UPSC Study Academy. Ever wondered how we see our reflection in a mirror or how telescopes reveal distant galaxies? Today, we'll delve into the fascinating world of optics, exploring the principles of reflection by plane and spherical mirrors, the versatility of convex and concave mirrors, and their applications in everyday life. Reflection with reference to light is the phenomenon where light rays bounce off a surface. According to the law of reflection, the angle of incidence, that is the angle at which the incoming light ray strikes the surface, equals the angle of reflection, that is the angle at which the light ray leaves the surface. This principle governs how images are formed by mirrors and other reflective surfaces. Reflection by plane mirrors. A plane mirror is a flat, reflective surface. When light rays hit the surface of a plane mirror, they reflect according to the law of reflection. This means that the angle at which the incoming light ray hits the mirror will be the same as the angle at which it reflects away. If a light ray strikes a plane mirror at an angle of 30 degrees relative to the normal, the perpendicular line to the surface, it will reflect off the mirror at the same angle of 30 degrees. Number of images formed. Number of images depends on. The number of images formed by two plane mirrors depends on the angle theta between them. The formula to calculate the number of images, n, formed by two mirrors inclined at an angle theta is n equals 360 degree divided by theta subtracted by 1. When two mirrors are placed parallel to each other, they produce an infinite number of images. This is because light can reflect back and forth between the two mirrors indefinitely. Size of the mirror. The size of a mirror refers to its dimensions, typically its height and width, which determine how much of an object or scene it can reflect. What size is required to see a full image? To see your full image in a plane mirror, the mirror needs to be at least half your height. This is because light rays from the top and bottom of your body need to reflect into your eyes. Even though the mirror is half your height, it reflects the entire body due to the angles at which light travels and reflects. Reflection by spherical mirrors. Spherical mirrors, with their curved surfaces, play a crucial role in optics. They come in two primary types, concave and convex. Reflection of a spherical mirror involves light bouncing off a curved surface, creating an image. There are two types, concave, which curves inward, and convex, which curves outward. Concave mirrors converge light rays to a focal point, while convex mirrors diverge them. The mirror's focal length is half its radius of curvature. The image formed can be real or virtual, depending on the object's position relative to the mirror's focal point. Differences between real and virtual images are outlined in the table. Formation. Real images are formed by the actual convergence of light rays. They occur when light rays coming from an object meet after reflection, creating a focused image. Virtual images, on the other hand, appear to diverge from a point behind the mirror. They are formed when the brain perceives light rays as if they were coming from an object's reflected image. Position. Real images are always formed on the opposite side of the mirror from the object. This means that the image appears behind the mirror. Virtual images are always formed on the same side of the mirror as the object. The image appears to be in front of the mirror. Nature. Real images can be projected onto a screen, meaning they can be captured and viewed on a surface. Virtual images cannot be projected onto a screen. While they can be observed through the mirror, they do not physically exist at the location where they appear. Size. The size of a real image can vary. It can be smaller, larger, or the same size as the object, depending on the positions of the mirror and the object. Virtual images are always the same size as the object. They maintain the same proportions and dimensions. Inversion. Real images are inverted, meaning they are upside down relative to the object. Virtual images are upright, meaning they maintain the same orientation as the object. Visibility. Real images can be seen with the naked eye. They are physically present and can be observed directly. Virtual images cannot be seen directly. However, they can be observed through the mirror and appear to be as if they were behind the mirror. Convergence of light rays. In real images, light rays converge to form the image. This convergence is essential for the image to be projected and viewed. In virtual images, light rays appear to diverge from a point behind the mirror. While they appear to diverge, they do not actually converge to form an image. Interaction with object. Real images can interact with objects. For example, in the case of a magnifying glass, a real image can focus light rays to burn an object. Virtual images do not interact with objects. They are merely optical illusions perceived by the brain. Location of object. Real images can exist beyond the focal point of a concave mirror or within the focal point of a convex mirror, depending on the mirror's curvature and the object's position. Virtual images are always placed within the range of vision of the mirror. They are located at points where the reflected rays appear to converge or diverge. Use of plane mirrors. Personal grooming. Plane mirrors are essential for personal grooming tasks like applying makeup or styling hair, providing a clear reflection for precision. Interior decor. They enhance interior design by creating illusions of space, reflecting light to brighten rooms, and adding decorative accents to walls. Optical instruments. In optical devices such as periscopes and telescopes, plane mirrors redirect light to enable observation or imaging over distances. Safety. They facilitate safety by providing visibility for drivers through rear-view and side-view mirrors, helping to monitor surroundings and avoid accidents. Art and photography. Plane mirrors are utilized in art studios and photography studios to manipulate light, create reflections, and capture unique perspectives in compositions. Concave mirrors. Concave mirrors curve inward and have reflective surfaces on the inner side. When parallel light rays strike a concave mirror, they converge to a point called the focal point in front of the mirror. This convergence is due to the mirror's shape, which causes light rays to reflect inward. Here are the characteristics of concave mirrors. Curvature. Concave mirrors are curved inward, resembling the shape of a cave. The inner surface is reflective, allowing light to be reflected inward towards the mirror's focal point. Focal point. When parallel rays of light strike a concave mirror, they converge at a point in front of the mirror called the focal point. This focal point is located halfway between the mirror's surface and its center of curvature. Real and virtual images. Depending on the position of the object relative to the mirror, concave mirrors can produce both real and virtual images. Real images are formed when the object is placed beyond the focal point, while virtual images are formed when the object is placed between the mirror and the focal point. Magnification. Concave mirrors can magnify images when the object is placed beyond the focal point. The magnification factor depends on the distance between the object and the mirror, as well as the mirror's focal length. Inversion. Real images formed by concave mirrors are inverted, meaning they appear upside down relative to the object. Virtual images, on the other hand, are always upright. Applications of concave mirror. Reflecting telescopes. Concave mirrors are used in reflecting telescopes to gather and focus light from distant celestial objects. They serve as the primary mirror, reflecting incoming light rays to a focal point where they are collected and analyzed. Reflecting telescopes offer advantages such as large apertures, compact designs, and minimal chromatic aberration, making them essential tools for astronomical observations. Dentistry. In dentistry, concave mirrors are employed as dental mirrors to provide dentists with a clear view of the patient's oral cavity. These mirrors help dentists examine hard-to-reach areas, such as the back of the mouth, by reflecting light and images. They aid in detecting cavities, plaque buildup, and other dental issues, allowing for accurate diagnosis and treatment. Makeup mirrors. Concave mirrors are commonly used in makeup mirrors to magnify the reflection of the user's face. By curving inward, These mirrors converge light rays to create magnified images, enabling precise makeup application and grooming. Makeup mirrors equipped with concave mirrors offer enhanced visibility and detail, allowing users to achieve desired cosmetic effects with accuracy. Searchlights and headlights. In searchlights and headlights, concave mirrors are employed to focus and direct light beams in specific directions. By reflecting light inward towards a focal point, these mirrors concentrate light rays, resulting in a bright, concentrated beam. This focused illumination is essential for applications such as outdoor lighting, automotive headlights, and theatrical spotlights, where visibility and intensity are critical. Ophthalmology. Concave mirrors find applications in ophthalmology for examining and diagnosing eye conditions. Ophthalmic mirrors, often referred to as eye mirrors or eye lenses, are used to reflect light into the eye during eye examinations. They facilitate the visualization of the retina, optic nerve, and other internal structures of the eye, aiding in the detection and treatment of eye disorders and diseases. Convex mirrors. Convex mirrors curve outward, with the reflective surface on the outer side. When parallel light rays strike a convex mirror, they diverge, spreading out as they reflect. This divergence causes the reflected rays to appear to come from a focal point behind the mirror. Characteristics of convex mirrors. Curvature. Convex mirrors are curved outward, resembling the exterior surface of a sphere. The reflective surface bulges outward, creating a wider field of view compared to flat or concave mirrors. Diverging reflection. When parallel rays of light strike a convex mirror, they diverge or spread out upon reflection. The reflective surface causes light rays to diverge away from each other, resulting in a virtual image being formed behind the mirror. Virtual image. Convex mirrors always produce virtual images, which are upright, diminished, and located behind the mirror. These images appear to be located at a point where the reflected light rays appear to converge. Field of view. Convex mirrors provide a wide field of view, allowing for a broader perspective of the surroundings. They are commonly used in applications where a panoramic view is desired, such as in rear-view mirrors for vehicles and surveillance mirrors for security purposes. Safety. Due to their wide field of view and ability to reflect light in multiple directions, convex mirrors are used for safety purposes. They help drivers monitor blind spots, navigate traffic, and avoid collisions by providing a broader perspective of the road. Rear-view mirrors in vehicles. Convex mirrors are used as rear-view mirrors in automobiles to provide drivers with a wider field of view, enabling them to monitor traffic behind and navigate safely by eliminating blind spots. Surveillance and security. Convex mirrors are employed in surveillance systems and security installations to monitor large areas such as parking lots, warehouses, and retail stores, allowing security personnel to observe activities from a central location. Road safety. Convex mirrors are strategically placed at intersections, driveways, and sharp curves to enhance road safety by providing drivers with a panoramic view of oncoming traffic, enabling them to anticipate and avoid collisions. Retail and store layouts. In retail environments, convex mirrors are used to improve visibility for staff, reduce shoplifting, and enhance customer safety by eliminating blind spots and facilitating surveillance of aisles and corners. Decorative accents. Convex mirrors are utilized in interior decoration to create visual interest, add depth to spaces, and reflect light to brighten rooms. Industrial safety. Convex mirrors find applications in industrial settings such as factories and warehouses to improve safety by providing wide-angle views of machinery, aisles, and intersections, minimizing the risk of accidents and collisions. Sextant. A sextant is a navigational instrument used for celestial navigation to determine the angle between the horizon and a celestial body, typically the sun, moon, or stars. It consists of a metal frame with a graduated arc, typically ranging from 0 to 120 degrees or more, and a movable index arm with a small telescope or sighting mechanism. The sextant works based on the principle of reflecting light from the celestial body onto a mirror and aligning it with the horizon, allowing the navigator to measure the angle of elevation or depression. By measuring the angle between the celestial body and the horizon at a specific time, along with known data such as the time of day and the observer's position on the Earth's surface, navigators can determine their latitude and longitude accurately. Sextants are widely used in marine navigation, aviation, and surveying, providing reliable means of determining position and course when other navigational aids may be unavailable or unreliable. Kaleidoscope. A kaleidoscope is an optical instrument consisting of a tube containing mirrors, colored glass, or other reflective materials arranged in a symmetrical pattern. When viewed through the viewing hole at one end, the colorful objects inside are reflected and refracted by the mirrors, creating intricate and symmetrical patterns that change as the kaleidoscope is rotated or shaken. The principle behind a kaleidoscope is the reflection and refraction of light. When light enters the kaleidoscope, it bounces off the mirrors multiple times, creating a series of reflections. The colored objects inside, such as glass beads or pieces of colored plastic, create different patterns as they move within the tube. These patterns are then reflected and multiplied by the mirrors, resulting in a visually stunning display of colors and shapes. A periscope is an optical instrument used to observe objects or scenes that are not in the direct line of sight. It typically consists of a long, narrow tube with mirrors or prisms at each end. The top mirror, known as the objective or upper mirror, is angled to reflect light rays from the desired object down the periscope tube. These light rays then encounter a second mirror, known as the eyepiece or lower mirror, which redirects them towards the observer's eye, allowing them to view the object. Periscopes are commonly associated with submarines, where they allow crew members to see above the waterline without exposing themselves to potential danger. By using a periscope, submarine operators can maintain situational awareness, navigate safely, and monitor the surrounding environment while remaining concealed underwater. Periscopes are also used in various other applications, including military vehicles, armored vehicles, and observation posts, where they provide a means of observing without exposing personnel to enemy fire or hazardous conditions.